This lesson is on radicals in exponential representation. Let's first consider the cube root of 64. So let's break it down. We got 64, which is made up of 2 times 32, which is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. You can see that we could rewrite this as the cube root of 2 times 2 times 2 times 2 times 2 times 2. What do we do when we take a cube root? Well, a perfect cube will simplify if it's got 3 of the same factors. So 2 times 2 times 2 forms 8, and the cube root of 8 is 2 because 2 cubed is 8. So essentially, you're looking for triplets in this case. So we've got one triplet of 2 and another triplet of 2's. Now, if you had rewritten 64 as 2 to the power of 6, which is what was actually happening here, you'd notice that in order to simplify this into 1 power of 2, we're going to look at taking triplets out of 6. So we're looking for how many groups of 3 are in 6, which is essentially saying how many groups of 3 are in 6. You're taking 6 and dividing it by 3, which means there are 2 groups of 2. There's 2 groups of 3, making each a 2, which leaves us with 2 to the power of 2. We have 2 groups of 2's coming out. And you'll notice, just like up here, this ended up giving you 4 and nothing under the root. This gives you 4 as well. So this is an interesting way of seeing a root, a radical. A radical can actually be seen as the denominator of its base's exponent. In general, you can see that any base x to the m over n will be that base to the m, the primary exponent, but then the root will be determined by the denominator of the exponent, because essentially the denominator is telling you what groups you're looking for, and that's exactly what the root number is telling you. When you saw the cube root, you automatically thought, I'm going to look for groups of 3 factors each. So, along with this information of relating a root to a fractional exponent, we also have our exponent rules, which you can pause the video and jot them down if you have forgotten them. But these rules are still going to apply. So when we multiply exponents with the same base, we're adding the exponents. When we say divide, we're going to subtract. When we take powers, we multiply. All of these rules have been determined in the past, and so take a read through them and remind yourself of them before you continue. The following examples are asking us to rewrite the expressions in radical form. So we're using our knowledge that x to the m over n is the nth root of x to the m. So that would mean that 5 to the 1/2 is actually the square root of 5 to the 1, which is the same as root 5. In the next example, the exponent of 2/3 tells us this will be the cube root of -8 to the power of 2. We can further simplify that because we know that -8 to the power of 2 is 64, and we, in the previous slide, saw that the cube root of 64 is 4. This next one here, you've got x squared, and then you've got y to the power of 1/2. And the power of 1/2, as in question 1, is actually just a square root. In the following examples, we're looking to convert these to exponential form. So we want to actually have the x to the m over n format versus the nth root of x to the m format. So here we have radical form, and then here we have exponential form. So here's the first example. We've got the square root of 2x. So that means we're taking 2x and we're taking the square root. So the square root means over 2, and we're actually taking this to the power of 1, so that's 1/2. Remember, square root is the same as an exponent of 1/2 because we're looking for how many pairs of the same factors we have in order to come out of the root. We can't really do much else with this except for write it as 2 to the half times x to the half. In the next example, we can further see how to convert from radical form to exponential form. Here we've got 2 times the cube root of 2, and a cube root is an exponent of 1/3. Now, since we have the same base here, we can actually combine the exponents. So we have 2 to the power of 1 times 2 to the power of 1/3, which is 2 to the 1 plus 1/3. Now we need common denominators to add fractions, so we're going to write this as 3/3 plus 1/3, which is 4/3. So that is now in exponential form. The next example, we have reciprocal given. Remember, a reciprocal is the same as a negative exponent. So this is really essentially the same as root 5 to the power of -1. If you're not sure of this, look back to the exponent rules to do with negative exponents. So we need this in completely exponential form. We still have a radical in here. So let's get rid of the radical. So root 5 can be written as 5 to the 1/2, as we looked at in the previous slide, and it's still to the power of -1. Exponent to the exponent will be multiplying, so we'll have 5 to the power of 1/2 times -1, which is -1/2. Next examples, we are asked to simplify. So we're going to do whatever we can to completely simplify the following. In this example, we have 100 to the power of 3/2. So we have 100 to the power of 3 being square rooted. So this is the square root of 100 times 100 times 100. If you'd really like to, you could write these each out as 10 times 10, 10 times 10, and 10 times 10. Each pair gives us 1 because the square root of each 100 is actually just 10. So we're left with 10 times 10 times 10, which is 1,000. In the next example, we have a negative exponent. The negative exponent sends it to the basement. It causes a reciprocal action to happen. So you have 1 over 27 to the 2/3. Now we can convert the 2/3 into a radical form. So that's actually 27 to the power of 2 with a cube root. So let's expand that and try to simplify that cube root. This is 27 times 27. Now if you notice that 27 is already a perfect cube, that's great. You can simplify the cube root of 27 actually becomes 3, because 3 times 3 times 3 is 27. The cube root of 27 is also 3 because of the same reason. So you're going to end up with 1 over 9. If you'd like to, you can rewrite these into the prime factors and notice the same thing happening. In the next example, we're combining some exponents. So here we've got a power to another power, so we're actually going to multiply the powers. That gives us 2/3 times 1/2. When we're multiplying, we don't need a common denominator. We just can simplify any common factors from the numerator and denominator. In this case, we've got 2 over 2, which is 1 over 1. That's 5 to the 1/3. You'll notice that that is essentially the same thing as taking the cube root of 5. In the next example, we have a numerator and denominator. They're all factored. There's no pluses or minuses. So we can simplify the 3 and the 9 by dividing them both by 3, giving us 1/3. Now we can further simplify the a terms because they have the same base and different exponents. And we can recall that you can actually take the subtraction of the exponents. So you have 1/3 a to the 2/3 minus 1/5. But in order to subtract these fractions, you need to have a common denominator. So our common denominator is the lowest common denominator, 4, 3, and 5, which is 15. So we got times 5 times 5. That gives us 1/3 a to the power of 10/15 minus, and then times 3 times 3. That gives you 3/15. So that's 1/3 a to the power of 10/15 minus 3/15, which is 7/15. You could also write this as a to the 7/15 over 3. Next up, we've got a multiplication and a division. So that's x to the power of 1/7 plus 3/7 over x to the 2/7. That gives you x to the power of 4/7, luckily it's the same denominator, over x to the power of 2/7. So we're just using our exponent rules here. So when we're multiplying the same base, we're adding the exponents. When we're dividing, we're subtracting. So here we're going to need to subtract 4/7 minus 2/7, which is x to the power of 2/7. It was nice to have the same denominator, otherwise we would have had to convert. This last example, let's look at simplifying the inside first. We've got a total cube on this, but inside we've got a division. When we're dividing the same base, we want to subtract. So we got 4/5 minus 2/15, and that gives us, and we need a common denominator, so times 3 times 3. So that's 12/15 minus 2/15 to the power of 3. And that gives us n to the power of 10/15 to the power of 3. You could simplify 10/15. 10/15 is the same as if you divide them both by 5, you get 2/3 to the power of 3. Now notice you're going to multiply 2/3 times 3. In doing so, the 3's will cancel, and you'll have n to the power of 2. Well, n squared is much nicer than this beast, isn't it?